Okay, so the last section we're going to talk about in Chapter 9. The last section we're going to talk about is how to approximate a function using what's called a Taylor polynomial. Now, these things are based on Taylor series, so the idea is using a Taylor polynomial, which is it's just part of a Taylor series, to closely mimic a function around a certain point for a certain interval. So let me start you off with this. Given a function, so let's say we have some function. What we know from our last section is that we can represent this function with a Taylor series. You remember talking about Taylor series? Hope so. We had spring break here recently, so hopefully that phrase is in your mind somewhere. So a Taylor series does this. It says, hey, if you want to represent your function of x, you can do it this way. You can start off with your function at some point that we've already said. So at point c equals 1 or c equals whatever I want. So we say, all right, well, the function of f of x can be represented by the function at c plus the first derivative of the function at c times x minus c. Do you remember doing this?
Yes.
Plus the second derivative at c times x minus c to the second all over 2 factorial plus, and we keep on going until we get to the nth derivative at c, x minus c to the nth all over n factorial. And then this thing keeps on going forever and ever and ever and ever, and that was called a Taylor series. So show of hands feel okay with the idea of a Taylor series. So what we said basically in the last section was, hey, you know what? We can represent a function with a Taylor series or a Maclaurin series. Of course, the only difference between a Taylor series and a Maclaurin series is that a Maclaurin series always has a center of what?
Zero.
Very good. Taylor series has a center of whatever I want. So a Maclaurin series is technically a Taylor series. So this says, hey, you know what? We can represent a function with a Taylor series. This is our Taylor series. Not a problem. Does a Taylor series ever end? No, it goes forever and ever and ever and ever and ever. And since it goes forever, say, okay, it's going to more closely and closely and closely and closely approximate our function for however far we go. Now, here's the idea today. Are you guys ready? Can we ever take a Taylor series and approximate it forever? Can we do that? Can you just do something forever? Probably not, right? You're going to have to end sometime because you're going to die unless you're a vampire, and then you're going to live forever. So you could probably... You probably do that. But, no, we're not. So, here's the idea for today. It says, well, a Taylor series goes forever. A Taylor series goes forever. Let's stop it. Right there. Let's stop it at the nth term. So, the nth derivative of f. Now, here's my question. Is this going to perfectly represent my function? Okay, let me start over. Somebody, I lost you. I know that your heads are probably like, a little bit. You need to wake up right now. Do you understand that a Taylor series goes forever? Yeah. It goes to this term and it keeps on going and going and going and going and going, right? So this would, I'm telling you right now, would perfectly represent your function. A Taylor series does represent the function if it goes to infinity. Now, if I stop my Taylor series at a certain point, is it a Taylor series anymore forever? No, it stops at a point. Is that, this whatever we have, this expression, we're going to give it a name in a second, is this expression going to perfectly represent my function if I stop it after a certain point? No. If a Taylor series does represent my function and I don't have the entire Taylor series, then this is not going to perfectly represent this anymore. Quick head nod if you understand that idea. I've stopped it. It's not the complete thing anymore. So, if this is not the complete Taylor series, do you know what? I stopped it. That's right. That's exactly. Just making sure you're paying attention, okay? Because I stopped it, it's no longer a Taylor series. But if you notice this, it is a polynomial. Do you guys see it? It's a Taylor polynomial. So this thing, when I stop my Taylor series at a certain point, what I end up getting is a Taylor polynomial of the nth degree. So this is an nth degree Taylor polynomial. Show of hands feel okay with the terminology here. So this right here is my nth degree Taylor polynomial. Now here's the issue. We just talked about it and said, well, you know what? Mr. Leonard said that if I had a Taylor series, yeah, it'd perfectly represent my function, but I don't have it anymore. I cut it short. Now I've got a Taylor polynomial. Well, the problem is there's going to be some difference between my Taylor polynomial and my function itself. Does that make sense to you? So basically, I've got this little extra. Over here. This little extra would be it's called the remainder of your Taylor polynomial. It really represents the rest of your Taylor series that would make this thing valid. Does that make sense to you? Mm-hmm. So it goes, okay, so imagine this. I'm going to start over from the beginning. A Taylor series goes forever. And we say, wait a minute, let's cut it short. I no longer have a Taylor series. This thing no longer perfectly represents my function. We call it a Taylor polynomial. Now, a Taylor polynomial is not going to exactly represent your function, but it's going to be a pretty close approximation. In fact, if I just have this little remainder, this little extra, what we can say is that the Taylor polynomial plus this little extra would make your function. So it's basically saying, hey, this thing's just missing a little piece. This little piece, that's your error. That's how closely, or how close you can get to represent your Taylor polynomial, as representing your function by your Taylor polynomial. This little extra piece, that remainder of your Taylor polynomial, that's your error right there. Show of hands if you feel okay with the idea. So is it an entire Taylor series anymore? No, we cut it short, we got a Taylor polynomial, we say, hey, you know what? That Taylor polynomial, it's pretty close to this thing, but it's not exactly the same thing as their function. We add a little bit of error, saying it's not exactly the same, but that little piece right there, that remainder is the error. That's how close you can make your function by representing it with a Taylor polynomial. Now, what I'd like to do is tell you explicitly what this error is. So it says, and I don't know if you need me to write this down for you, but this says that your function can be represented by a Taylor polynomial, this nth degree Taylor polynomial plus some sort of an error. Now here's our error. Let's look a little more closely at this. If we were to just continue my Taylor series, now keep in mind, this is no longer a Taylor series, okay? We have cut it short. Does that make sense to you? We've cut it short. So this is now a Taylor polynomial and the error. The error, though, if you just continued this would be, well, what would the next derivative be? Yep, the n plus 1 derivative at... Now that's where we're going to make a little change here. We're going to say it's at z, and I'll tell you why in a second. So keep in mind that's a z, not a c. X minus c to the what power is that going to be?
N plus 1.
Very good. All over what, everybody?
N plus 1 factorial.
Perfect. This is the rest. So this is going to represent the rest of our Taylor series, which we kind of cut off. So we're saying, hey, you know what? That is the remainder that we're going to get. If I cut off my Taylor series, you go, I have my Taylor polynomial, and then I'm going to have this little extra. The rest of my Taylor series is represented by this piece. I'm not going to prove it. You can look up the proof if you want to. You know, to kind of take my word for it right now that we can do this. The logic behind it is that if you cut a Taylor series short, it no longer perfectly represents your function. A Taylor series would. So we call that place where you cut it off, that's the end of our Taylor polynomial. Now, there's going to be some difference between the Taylor polynomial and your function. We say if I add a little bit to it, then I can make it exactly the same. That's your error. We're going to use this in a little bit to approximate how close, to say how close our approximation is to our actual function. Have I made sense of this at all for you? It's going to make a little more sense when we go through an example too. So, basically we're taking part of a Taylor series as an approximation. Now let's talk about the z. That z right there, that z is some number between c, the point you're using, and x, the point you're trying to approximate. We get to pick what z is, and we're going to do this in a minute. Z, you're going to pick z so that you get the largest error. Are you listening? You don't want to underestimate your error. You want to overestimate it if that's the case. Okay, you don't want to underestimate it. So we get to pick z. Z is some point between c and x, between the point you're using and the point you're trying to approximate. And let me illustrate that right now with an example. Are you guys ready for an example? Mm-hmm. Okay, so Here's what we're going to do. Let's say we've got a function. Our function is ln x. And what we're going to do is we're going to approximate ln of 1.1. Now, if you're thinking, wait a minute, didn't we just kind of do this in the last section? Didn't we have these Taylor series where we could approximate and find out endpoints, all this stuff for interval? Well, we did that, right? Well, but that took a long time, correct?
Yes.
This is kind of like a shortcut. This is saying, well, let's approximate, but maybe we don't have to find the entire Taylor series or Maclaurin series or whatever. Let's go ahead and let's do an approximation really, really fast. And that's what this is for. Taylor polynomial says, let's approximate this quickly. Here's how we're going to go about doing it. So our idea is we're going to find a Taylor polynomial at something that's close to this and then use it to approximate. So our idea, we want to find a Taylor polynomial at some point close. Now, let's pick a good point that's really close to the number we're trying to approximate. What number are we trying to approximate here?
1.1.
Yeah, ln of 1.1. Give me a number that's close to 1.1 that would be easier to work with.
1.
Okay, that right there, that is your c. Does that make sense? Your x in this case is 1.1. Look at f of x, your x is 1.1. Do you guys get that? So your x is 1.1, your c is going to be 1. So we're going to find the Taylor polynomial at some point close. Let's say c equals 1. And here we're going to use a 4th degree Taylor polynomial because I want to show you how it works, all right? Now, I got to be honest with you, on any test or any homework that you're going to have, they're going to tell you what c to use, you don't get to pick it, and they're going to tell you what range you're going to have, and they're going to tell you what degree you're going to use. Does that make sense? So it's not going to be up in the air like this one is. I'm just showing you, like, in real life how you go about it. You go, okay, well, tell you what, I want to approximate this, let's use a Taylor polynomial. Let's use it at a point that's close. Hey, 1 is pretty close to that. You with me? And let's pick the 4th degree because I'm pretty sure at that point we're going to have an approximation that's fairly good. So find some Taylor polynomial that's close, at some point that's close, equals 1, and then we're going to use a 4th degree Taylor polynomial to do this. The rest of it is honestly pretty easy. There is no pattern to find. Remember the patterns that you guys just had to do in your homework that were kind of hard to find sometimes? You don't have to do that here, and that's what's kind of nice about this. There is no pattern. All we're going to do is start like you would do a Taylor series, but then you're just going to stop. So we start with, okay, can you do a Taylor series from this? Sure you could. What's the first thing you did when finding out a Taylor series? What would you do? All those derivatives you had. So we're going to start with, can I erase this here? It's right my way. Okay, so, well, let's start with f of x. What's f of x?
ln of x.
How about f prime of x? Good. Do we need to keep going?
Yes.
What degree Taylor polynomial did I say?
4th.
So what derivative you got to go to?
4th.
You're kind of close. We'll get there. Second derivative is? Good. How about third derivative?
-2.
Say again?
Is it?
I'm going to assume you said 2 over x cubed. Let's get our brains working today. How about that one? How about the fourth derivative? -6 over. Okay, you guys with me on this one? We know derivatives, yeah? All right. Just make sure. Just make sure. I know spring break takes a lot out of our minds sometimes. It does mine, I tell you that. So stop drinking, all of you, just so you know. So, function, this is a Taylor series, right? This is how we start Taylor series. We do the function, we do a derivative, then a second derivative, then a third derivative, then a fourth. And with a Taylor series, we keep going. and we'd find a pattern for this. Show of hands feel okay with that one. Now, we stopped at the derivative of 4. Why did we do that? So degree 4. Now, here's the thing. Do you understand that with a degree 4, I erased it, but the next term was my error, right? Look up here. The next term was my error. If I have a degree 4, what's this one going to be?
5.
Find your next derivative because you're going to use it for your error. So I'm going to leave this at, this is all we need for my polynomial, okay? For my error, I'm going to go, okay, I need one more. Just hang on to this in the back of your head because we're not going to use it right now. We're going to use it in just a little bit. Show of hands feel okay with that so far? Okay, do you understand why we're finding the next derivative past our degree that I've told you? What's it for?
Error.
That's exactly right. Now, the next thing we did with the Taylor series, you said, all right, well, cool. What do we do now? With the Taylor series, what did you do? You plugged in C. Oh, very good. Do we have a C? What's our C?
1.
C. So if we plug in C equals 1, then we have f of 1. And we have f prime of 1. And so forth. And so on. And we're even going to do it down here. So let's plug that in. Let's see what we get. How much is f of 1, please?
0.
How about f prime of 1? We're going to get.
1.
How about f double prime of 1?
1.
Triple prime?
2.
Quadruple prime?
6.
And?
1.
Perfect. Y'all still okay with that so far? Now, don't make it harder than it is. You're not looking for a pattern here. I don't care about the pattern. What we're doing, remember the very beginning of when I explained this, I said what we're doing here is we're taking part of a Taylor series. That's called Taylor polynomial. We're taking part of a Taylor series, our Taylor polynomial, to represent or approximate our function. It's going to be an approximation. We don't have to find the whole series. You stop right here, and then you start building your polynomial. So here's what we're going to do at this point. Are there any questions on, you know what, I'll do it down here because I want to make sure you see all this together. So from right here, after we found our derivatives, after we plugged in our C, we're going to go ahead and do our 4th degree Taylor polynomial. This right here stands for your 4th degree Taylor polynomial. Now, I'm hoping that you remember what Taylor polynomials are because they are based right off of the Taylor series. So basically, we just got to take this stuff and plug it into here. That's all we got to do. So a Taylor polynomial would look like this. It would be, it'd start with f of c. But what is our c in our case?
1.
F of c would be,
1.
yeah, f of c would, f of 1 would be 0. So we'd have f of 1. Are you guys with me on this? Are you sure you're with me? I don't want to lose you right now, right? We've been doing this for a while now. Plus, what's the next one?
F prime of C.
Okay, f prime of 1, and then you would have x minus,
1.
you're right, it's x minus c, but in our case our c is 1. Are you okay with that one?
Mm-hmm.
Okay, what's the next one?
F double prime of 1.
And then you would have over? Yeah, it's 2 factorial. I'm going to change that to 2 in just a second, but just so we have the pattern here. Keep on going. What next?
Triple prime.
X minus c to the, so we're going to have x minus 1 to the 3rd. All over 3 factorial. Plus, keep on going. What is it?
F triple prime of 1.
Oh, we have the triple prime.
F, yeah.
Okay, let's see if we're all okay with that one so far. I want to really make sure. So we start off, basically a Taylor polynomial is just part of a Taylor series. So we're practically doing the same thing, but it's easier. It's easier because we don't need to find a pattern. All you got to do is, hey, find out whatever derivative that you need. So if I say degree 4, you're going to find out the fourth derivative, yeah? Plus 1. The plus 1 is for your error. Quick hit, if you're okay with that one. Plug in the point, no problem. You're going to have the c. I told you what it is here. Generally, it's going to be given to you. So plug in your c. Not a problem. Do you see that this is exactly the same as the Taylor series so far? Find these points, no problem. Now, make up your Taylor polynomial. The Taylor polynomial don't need a pattern because it stops at a certain degree. It's finite. It does not go forever. So if I say find the 10th degree, yeah, that sucks, but at least you're going to be able to do it and stop somewhere. Does that make sense? Does not need to go to infinity. So if I say 4th degree, well, here's the 0 degree. 1, 2, 3, let's stop at 4. 4th degree Taylor polynomial says we stop at the 4th derivative. It's a degree 4 polynomial. You see the degree 4 I'm talking about? That's what it is. Making sense so far? Now, might want to simplify it. Do we know what f of 1 is? And f prime of 1 is?
Yes.
We know what all those things are. Plug in those numbers. So let's do that. I'm going to leave this here. I'm going to work down here for a second. Unfortunately, these boards are quite small. So the 4th degree Taylor polynomial, sorry, I forgot my x here too, is, what's the first thing we're going to start with?
1.
0.
0, yeah. And then what?
1.
Yes, so if it says f prime of 1 is 1, then right here we have 1. So what's our first? And then we're going to go, okay, now let's add to it. F double prime of 1. What's f double prime of 1?
-1.
Oh, okay, so we're going to have minus x minus 1 squared over 2 factorial is simply 2. Okay, we can do that. What's after that?
2.
Yeah, let's do f triple prime. F triple prime is 2, but it's still plus. So plus 2
Times
x minus 1 to the over.
2 factorial
Perfect. Okay, and then where are we at now?
minus.
Minus. Why are we having a minus here?
-6.
So we're going to have minus 6x minus 1 to the 4th over 4 factorial. Do we go any further than that right there?
No.
Okay, show of hands, feel okay with that so far. So, all we've done, we've taken these numbers, we plugged them into their appropriate spots in our 4th degree Taylor polynomial. This is exactly what we have. Simplify this stuff. Make it easy. Remember, what we're doing here is we're going to use this Taylor polynomial as an approximation. What that means is that we want it to be easy to plug a number into. So, let's do it. So if we make this easier, 0 is gone, we get x minus 1, we get minus x minus 1 squared over 2, we get plus. Do you see that this is going to be 3 times 2 times 1? Our 2's are going to simplify. I'm going to get
3.
x minus 1 to the 3rd over 3 minus, do you see that this is 4 times 3 times 2, and this is 3 times 2?
4.
Do I keep going?
No.
No, Taylor polynomials stop at whatever degree I say, or whatever degree the problem says. What I want to know is, show of hands if that one makes sense to you so far. Okay, so yes, no?
Yes.
You see where all the things come from? So now here's the plan. If this is the 4th degree Taylor polynomial, basically it says we've stopped our Taylor series after 5 terms. The first one is no derivative. So after 5 terms, we've stopped. You got me? This is going to be an approximation. Now, how good? We're going to determine that in a minute. But you can approximate it. Notice what it says. It says we base this on something that's really close to the number we're trying to approximate. Our C was 1. That's really close to 1.1. So if I wanted to approximate ln of 1.1, here's what it says. It says that this Taylor polynomial, this degree 4 Taylor polynomial, represents or approximates this thing approximates f of x equals ln x around the number 1, because it was centered at 1. Does that make sense to you? So, if we want to approximate ln of 1.1, all we need to do is plug in 1.1 to our Taylor polynomial. Does that make sense?
Yep.
I'll say that one more time. What we've done so far is said, hey, you know what, we've got a Taylor series, let's cut it off. That's going to be an approximation. So this cut off Taylor series at the fourth derivative says that our fourth degree Taylor polynomial is going to approximate the function where we got that thing from around a certain point. That certain point that we picked was around the point c equals to 1. So while we have an x minus 1 up there, that's our center. Quick head nod if you're all right with that one. So if I wanted to find ln of 1.1, all I have to do is plug in 1.1 for my, yeah, if this is f of x equals ln of x, and I want to find out 1.1, this x, that's this x. So if I want to approximate ln of 1.1, all I've got to do is find p sub 4 of 1.1. What that ends up being is 0.1 minus 0.1 squared over 2 plus 0.1 to the third over 3 minus 0.1 to the fourth over 4. Now this is an approximation for ln of 1.1. I got to make sure that this all makes sense to you because I'm, of course, your teacher here. So, do you guys get the idea that if I cut a Taylor series short for a Taylor polynomial, it's an approximation?
Mm-hmm.
Do you get the idea that if I want it to be close to a certain number I'm trying to approximate, then that's what my center is going to become? So here our center is 1 because it's really close to 1.1. All right, well, do you also understand that if I want to approximate my function, all I have to do is plug in the number into my Taylor polynomial? Do you guys get that idea?
Yes.
So if I were to work this out on the calculator, whatever this is, it's going to be pretty darn close to ln of 1.1. Now, we of course have calculators, right? So let's do 1.1 ln. But it's kind of cool that we can also approximate it with a Taylor polynomial. Isn't that nice? This has no ln whatsoever. It's just based on the derivatives of ln x. That's interesting. Now, here's the issue that we're going to have with this. The issue is this an approximation? Yeah. How good of an approximation is it? That's where the error comes in. So here's what we're going to do next. We're going to find out the error of this approximation. Are there any questions on any of this? Question?
Do you always go to the fourth degree, or did you just
No,
for this one?
I chose it just for this problem. Hopefully it makes sense to you that the larger degree Taylor polynomial you go to, the more accurate your approximation is. If I did a first degree Taylor polynomial, well, that'd been not so much, right? So second, third, we're going to use seconds, we're going to use thirds, fourths, whatever. Usually people don't go much past that because it just gets a little tedious. But I picked 4 just because it came into my head, okay? And I wanted to show you the process. I think if I just did a first degree, it really you wouldn't see a lot.
Which is actually one.
Okay, so now for our error. Well, our error, I'm going to start from the beginning on the error. I'm not going to use anything that we've basically done. We had it up here, but I'm going to show you from the beginning. And you're going to see that you could have just taken what we had right here and gone with it. Our error from a fourth degree Taylor polynomial, that's a remainder, it's called the remainder. So the remainder of a fourth degree Taylor polynomial. Well, what that's going to be is that's going to be the next derivative at some point z. Did I talk about z before?
Yes.
Did I talk about how z is between c and x? X, what's our c?
1.
We're going to plug that in a minute. Of the next power over the next factorial. Now, it's your job to start plugging these things in. So here's what we're going to do. we're going to start simplifying this. So the remainder of the fourth degree Taylor polynomial is the fifth derivative at z, some point between c and x. X minus, we already had our c, use the same c. You guys okay with this one so far? What piece of this do we know? Okay, we know that one. What about that? Do you know what the, let's start here. Do we know what the fifth derivative of x was? You had that already, right? Because I told you to go one more derivative than we already had. That. Otherwise, you'd have to start from the beginning right now. I don't want to do that. This was, if I'm 24 over x to the
Fifth power.
You guys okay with that one? Which means that the fifth derivative of z is simply 24 over z to the fifth. So fans feel okay with that one? Now here's your deal. You get to pick z. You're going to pick z such that you get the largest error. The largest error. Now keep in mind, z is a number between, what two numbers did I say?
X and Z.
Is a number between c and, what's our x? Yes, that's exactly right. So z is a number between those two values, c and x. So if you understand that concept. Okay, now here's the deal. You need to pick which one of these, it's usually going to be one of the endpoints here. You need to pick which one of these things is going to give the larger value when you plug it into here. This does not change. Okay, this is going to be 1.1. Do you see why it's going to be 1.1? How much is your x? This is going to be 1.1. This c, it's already there. It's going to be 1. Does that make sense to you? So you're going to get 0.1. That's not going to change. That's not going to change. This is the only thing that has a possibility of changing because it's in an interval of numbers. So you're going to pick the z for which this thing is biggest. Now look here, this is the only thing that can make this bigger or smaller, okay? The x is chosen. What would you put here to make this larger? Would you put 1.1 or would you put 1?
1.
You put 1. So in our case, we're going to pick z equals 1, because that's going to give us the largest error. Quick hit now if you're okay with that one. Okay, so we're going to pick z equals 1 for the biggest error. You don't want to underestimate the error. So in our case, the fifth derivative of f at z would be the fifth derivative of f at 1. What's the fifth derivative of f at 1 when I plug in 1? How much is that going to be? Say it again. It's 24 over 1 to the fifth, just 24. By the way, you're going to notice something. Some students have an issue with this. You go, wait a minute, why did I plug in 1 here, but I'm plugging in 1.1 here? You can have different values for x and z. They don't have to be the same. Okay, so sometimes your z will be the same as x. Sometimes your z will be the same as c. Your z just has to be between those numbers, and you pick it such that you get the biggest error possible. Show of hands? Okay, now, here we go. Let's put this all together. So if I know that my error is equal to the fifth derivative of f at z, some point between x and c, and this value of z equals 1 gives me my biggest error, I'm going to have 24. This gives me 24. I'm going to have, what's my x going to be, everybody? 1.1 minus 1 to the fifth all over 5 factorial. So in our case, if you notice this, and this works out for this one quite nicely, 24 is 4 times 3 times 2 times 1. This is 5 times 4 times 3 times 2 times 1. So if I simplify that, I'm just going to get something over 5. In fact, I get 0.1 to the fifth power all over 5. And that's equal to, someone with a calculator, tell me what that is. 0.1 to the 5th divided by 5. So 0.05 zeros or something. Don't leave me hanging.
2 times 10 to the negative 6th.
There you go. Thank you. Now, I said this goes fast, and they do go fast. I just had to explain this to you, but this does go quite quickly, because all you got to do is do a few derivatives, and then you're going to plug in a number, and then you're going to find an error. So here's what we just said. Are you with me?
Mm-hmm.
Okay. We cut a Taylor series short. It's called Taylor polynomial. There is some sort of error associated with that. With our Taylor polynomial, all you got to do is plug in a number you want to approximate, as long as you base that Taylor polynomial around the number. So in our case, we base it around 1 because we're trying to approximate 1.1. Just plug it in. By the way, has anyone worked this out? Did you do it? How much is it?
0.095308333.
Assuming you're right. I'm not going to double check you. So assuming that you're right, that approximation is within this number of what this really is for ln 1.1. I'll say that one more time. When you work that out, when you work this out, you find it. This is within this distance from what this actually is. So is this an approximation of this? Yes. How close is it? Now we know. It's within 0.000 tenths, hundreds, thousands, 10,000s, 100,000, within 2 millionths. So that's pretty darn close. So fans feel okay with that idea. Let's do another example while this is fresh in our heads right now. It's an interesting idea though, isn't it?
Yeah.
Imagine if you didn't have calculators and you had to be extremely close with your value, and you didn't know what ln of 1.1. ln of 1's easy, it's 0. But ln of 1.1, how are you going to do that without a calculator? How would you do it? I would probably use a Taylor polynomial and just do it to like the 10th degree. It's going to be super freaking close, and you can prove how close it is. That's interesting. Okay, let's try another one. Let's do the square root of x. Here's how your test question is going to look. What I want is find the second degree Taylor polynomial at c equals 4, and I want the error on a given interval. By the way, if my c equals 4, do you follow that my interval is probably going to be somewhere around 4?
Mm-hmm.
Yeah. In our case right now, it's going to be 3 to 5. Plus you. This is how it's going to be worded for you guys. So it's not going to, I kind of made up the last one to give you how you would do this in real life, okay? You pick something close to it, and you go for it. For us, it says, all right, tell you what, I want a second degree Taylor polynomial. I want you to find this Taylor polynomial centered at c equals 4, and I want you to find the error if I approximate something between 3 and 5. This is what this means. So when you find the error later on, it says, you know what, tell you what, give me any number between 3 and 5 inclusively, plug it into your Taylor polynomial, and I guarantee the error is going to be less than blank. Does that make sense to you? So within this interval, we have a maximum error. You get it? That's why we pick the number that gives us the biggest error here. So let's continue. How do we start? Yeah, just like a Taylor series. So we're going to have f of x. We're going to have f prime of x. Actually, you know what? In fact, it's probably going to be a little bit easier just to do it this way. Let's see. What next? Do we need to keep going?
Yes.
How much is it?
-1/4.
Uh-huh. Do I have to keep going?
Yes.
Do I have to keep going for my Taylor polynomial?
No.
Do I have to keep going for my error?
Yes.
Okay, so I'm going to write this down here. I'm going to leave this one. 1, 2, 3. A third derivative. We go one more derivative than whatever degree I want because that's going to give us our error. That's all. So here we're going to have, what is that, positive 3/8?
Yeah.
X to the negative 5 halves. All right, well, that's cool. Now what? What is our C in our case? So what we want is we want f of 4, and we want f prime of 4, and we want f double prime of 4, and ultimately we're going to have f triple prime of 4. Okay, come on, I want your help with this real quick. What do we get?
2.
2, very good. What's next? 1/4, you're right. What's next?
-1/32.
I think so. Do you know how we're doing those ones? This is -1/4 times square root of 4 to the third. So you take the square root of 4, that's 2 to the third power, that's 8. 8 times 4 is 32, it's -1/32. Let's do this one. So this would be, oh man, is that a little nasty? How much is that? Square root of 4 is
2.
2 to the 5th power times 8, whatever that happens to be. What is it?
3 over 256.
256.
Dang, yeah, okay. Okay, we'll hang on to that one in our memory banks here real quick. Now, do we need to find a pattern like a Taylor series?
No.
All we gotta do is write out the first, when I say degree 2, you're gonna have 3 terms then. You're gonna have f, the first derivative of f, and the second derivative of f, because we're in a degree 2 polynomial. So let's do it. If we do this, our Taylor polynomial of the second degree is going to be f of 4 plus f prime of 4
X minus 1.
Square. Oh, I'll make the next one square.
Next one squared, you're right. All over 2. And then we start simplifying it. F of 4, okay, that was 2. Plus f prime of 4, that was 1/4 x minus 4. Plus, if we wanted, let's see, the second derivative, oh my gosh, it's going to be a minus. Minus 1/32. So what's that going to give us all said and done?
1/64.
That's right, minus 1/64. X minus 4 squared over 64. I want to make sure you guys are okay with this. So f of 4 was 2, no problem. F prime of 4 was 1/4, we get 1/4 x minus 4. Okay, well, this second derivative of 4 is -1/32. Are you with me?
Mm-hmm.
-1/32 times 2 is -1/64, x minus 4 to the second power, not a problem. This answers the first part of the question. Did I tell you to approximate anything?
No.
All I wanted was a Taylor polynomial of the second degree at c equals 4. That's this. This is the Taylor polynomial of the second degree at c equals 4. You guys okay with that one?
Mm-hmm.
Now, this can be used to represent, or to approximate, I should say. This can be used, here's the idea here. This Taylor polynomial can be used to approximate this function on anything around 4. Does that make sense to you? Do I need to write that down for you? No? Okay. You sure? So you might want to write that down. This Taylor polynomial can be used to represent or approximate this function on anything around 4. Why around 4? That's our center. Now, what we're going to do is say, imagine you used it to represent or approximate a number between 3 and 5. We're going to find out the largest error after, probably next time we come back. So I'll write this out real quick and then we'll stop here. So this can be used to approximate our function around 4. The next step is we're going to find the maximum error between numbers, so for numbers between 3 and 5. So you're going to say this, I want to plug in 3.1, or I want to plug in 4.9, I want to plug in 5, whatever, I want to plug in 3. We're going to say, okay, whatever number you want to plug in between 3 and 5, I'm going to tell you that this Taylor polynomial, whatever you plug in, is going to be within a certain range, it's going to be within a certain error. We'll do that next time. You're going to copy me. Okay, so so we're finding the Taylor polynomial of functions now. So the Taylor polynomial is part of the Taylor series. We stop at a certain degree. That means if I want a degree 2, we're going to stop at the second derivative, and that now becomes, instead of the whole Taylor series, which perfectly represents our function, we're stopping. That means it's an approximation. So it's a two-part idea. Find the approximation, the Taylor polynomial, then find the error. The error says whatever you plug in, it's going to be within this amount of what the actual function is at that point. We've made it this far. We've done the Taylor series idea. We said, okay, here's our function, first derivative, second derivative. We always go one more derivative than the degree I'm asking you for. And the reason that we do that is because we use that next derivative in our error. So the error is the next term, basically, in a Taylor series. So what we say is, okay, Taylor polynomial, we're stopping at the second degree, no problem. We have f of 4. Why do we have a 4? Where's that coming from?
Degree of 4.
Not the degree of 4, but the c, the center of 4. So we have 4, okay, first derivative of 4, second derivative of 4, no problem. Plug those things in, and this is where we got last time. Got it?
Yeah.
Now, what we need to know is that this thing right here, this is a Taylor polynomial of the second degree, what I'm asking you for. We have all of our numbers plugged in except for our x, that's great. This can be used to represent our function, or approximate our function at any number around 4. Why around 4? Because that's what I told you to center it at. That's why it is x minus 4. So what I said is, okay, if that can be used to approximate f of x around 4, what's the maximum error that we will have if we plug in the numbers from 3 to 5? So if we plug in like 3.01, if we plug in 4.2 or 5 point whatever, what's the biggest error that we could even get? And that's the idea of the next thing that we're going to do. So we don't end with our approximation. This is actually really, really easy to get. All you got to know how to do is do a few simple derivatives and know the formula. The formula is a piece of cake. It's the function at whatever your center is. The first derivative at your center, and then x minus 4. The second derivative at your center, x minus 4 to the second over 2. And the next one would be x minus 4 to the third over 3 factorial, and so on, and so on, and so on, until you reach the degree I want. Now the error of a, sorry, this should be a 2. The error of a second degree Taylor polynomial says, all right, you're going to start with the next derivative. So if I have a second degree Taylor polynomial, the error, the remainder of that, starts at the third derivative. That's why we go ahead and find that, because we're going to be using it. Starts with the third derivative of, is it an x?
Z.
It's a z. Z is some number between c and x. So between c, the center, and some number that you are approximating. We're going to talk about that in a minute. Then we're going to have x minus 4, no problem, to the your degree's 2, correct?
Yes.
That means that your remainder is going to have a power of 3 to it. Over 3 factorial. Those things match. Quick head nod if you're okay with that so far. Okay, let's go back and look over here, because right now I don't know the number I have to plug in here, so I'm not going to plug in 3, I'm not going to plug in 4, I'm not going to plug in 5. I think I did that last time just to give you an exercise, but we're not actually going to do that. We're going to be smarter about this, because what we're trying to find out is what, the smallest possible error or the largest possible error? Yeah, the largest. The smallest would be, well, if you plugged in 4 exactly. You get the smallest error. But if you plug in anything outside of that, naturally we're going to get an error. So, what we're going to do is go back over here and say, all right, if this is our third derivative of f at x, then what that means is our third derivative of f at z would simply be this same thing with a z instead of an x. Does that make sense to you? Hello, you with me, guys?
Yes.
Okay, so this is, all right, well, the only reason why we did this third derivative was now for our error. We didn't use it in our Taylor polynomial. Well, now let's make a little substitution. So if I know that the third derivative of f at z gives us this thing, then I can translate this to the remainder of the error of the degree 2 polynomial, Taylor polynomial is, instead of the third derivative of z, I'm just going to put this. I'm going to put 3 over 8 z to the 5/2 times x minus 4 to the third over 3 factorial. No problem. Quick show of hands if you feel okay getting that far. Show of hands if you do. We already talked about the formula for the error, the remainder. It's just the next derivative, the next degree over the same thing. Degree matches your factorial. Cool deal. Well, we've gone ahead and said, well, you know what? The degree 3 remainder is going to have a third derivative of f. We've already done that. This was at x. You just plug in z, not a big deal. Now is where you do something that's kind of important to find your error, your maximum error. You pick the numbers that are going to make your error the biggest. So look back over here. We have centered at 4, very good, but we're on the interval from 3 to 5. Now, your x is going to be some number between 3 and 5. You're going to pick the x that gives you the biggest error here. Your z is going to be some number between 4, it's somewhere in here, somewhere between 4 and your x. Now, keep in mind, your x ranges from 3 to 5. So you can pick x between 3 and 5, and you can pick z between 3 and 5. Pick them so that your error becomes the biggest. Here's what I mean by that. Your x, in order to make this the biggest, because, hey, this is centered at 4, right? That's right in the center of your interval. It doesn't matter what your x is. Your x can be 3, or your x can be 5. Don't pick anything between there, because that's going to give you a smaller difference. Does that make sense to you? If you picked 4.01, yeah, your error is going to be very little, because it's only going to be 0.01. Pick your end point, either 3 or 5. Pick it so that this difference is the largest, okay? Now, if you pick 3, you're going to get -1. Put an absolute value around your remainder to make it positive. So you can do that. So if I pick x equals 3, that's fine. You notice how you get -1 out of that? -1 to the third would still be -1. Just take your absolute value. Your error, if you get a negative, it doesn't really matter, because all your error is saying is that your answer is going to be within this amount. That within this amount is kind of like a measurement. It's like an absolute value anyway. So if you want to keep it positive, cool, pick the 5. If you don't care about it, do absolute value, pick the 3. What I'm trying to tell you is that pick the endpoint, if there exists one, that gives you the maximum distance here. Not sure if you understand that idea. I'm going to pick the 5, just to show you that the x does not have to be the same as the z. I'm going to pick the 5 for the x. Now the z. You need to pick one of these numbers in here that gives you the biggest error possible. If I picked 5 for my z, would it be the biggest error or the smallest error?
Smallest.
What would be the biggest error?
3.
Because if I'm dividing by a number, dividing by a smaller number gives me a larger fraction here. Does that make sense to you? So, here's what we know. We know that z is somewhere on 3 to 5. So we're going to pick the z that gives us the largest possible error. So our error of our second degree Taylor polynomial in this case is going to be when we use 3 as our z. So if I were to approximate my function at the number 3, so if I were to plug in 3, that's going to give me the answer that has the most error. Make sense to you? Anything more than that, like 3.01 or 4 or 5, that's going to give me a smaller error than if I were to plug in 3. So to say this is the maximum error that we get, we're going to use that 3. It gives us the biggest fraction. What was I going to use for x here? Yeah, 5 or 3. It doesn't really matter, because you're going to get 1 or -1. You just want to pick one of those endpoints that gives you at least that the biggest value in terms of absolute value. So I picked 5 to keep it positive. It's all good. So what this all works out to, well, the 3 and the 3 factorial, again, to simplify, you're going to get 2, let's see, here's 1 to the 3rd, that's 1. That gives you 2 times 1, so that's 2 times 8, that would be our 16 times 3 to the 5 halves. And that's roughly, can someone do that for me? Tell me what that is, roughly.
About 249.4.
Say what now?
249.4.
It's got to be a decimal.
Must have confused.
0.004.
0.004, let me get a double check on that, 0.004.
I agree.
Well, if Rob agrees, it must be right, so. Hopefully I did my math right. Did I do my math right? Did you check it?
Yeah.
If this is 3 times 2 times 1, then our 3's are gone, and we get 2 times 8, that's 16, we have this. And you did, on your calculator, I'll make sure you did this right. You did 3 to the 5 halves power, right? And then you multiplied by 16 after that, correct? And you got 0.004. Okay, so here's what this says. Assuming that the math is correct, here's what it says. It says, all of this put together says this. It says that this is your secondary Taylor polynomial. This can be used to approximate this function at any numbers around 4. In fact, if you pick numbers between 3 and 5 inclusive, the maximum error that you will get is 0.004. That says that any answer that you get using this, is within 4 thousandths of the actual value of this function at whatever point you plugged in. Show of hands if you feel okay with that one. That's the idea. Now, what I'd like you to do is, since you guys are working out of a calculus textbook, read the other examples. I obviously can't go over all of them in class, but this is basically the idea, and I think, hopefully, I've explained this well enough for you to understand the idea. Do you guys get it? The basic idea is, well, take a Taylor series, take part of it. It's called a Taylor polynomial. It will have an error because you're not taking the whole Taylor series. That error is really easy to find. It's just the next term after you stop at whatever degree I've told you to. You can find that by making it the biggest possible error, and that's the maximum error you can get from a Taylor polynomial when using it to approximate your function. Okie dokie? Now, I want to talk about something else. I want to talk about how to determine when a function can be represented by a Taylor series. That's the next thing we're going to do. That's not a super hard concept, but it's a little bit different. By the way, are there any questions on this one as I'm erasing the board? Okay.
Rewind.
Yeah, just rewind it. Hey, that'd be so cool if I could actually do that in real life. So, when does a function have a Taylor series representation? When does a function have a Taylor series representation? Well, let's think about it this way. Let's use what we know about Taylor polynomials. If we have a Taylor polynomial, then that Taylor polynomial is going to have a remainder, isn't it? So if the remainder of a Taylor polynomial is this. It's the remainder of whatever degree Taylor polynomial we have given a Taylor series. So we have this r sub n of x. Here's the idea. If the limit of your remainder goes to 0, if the limit of your remainder from your Taylor polynomial goes to 0, then our function can be represented by a Taylor series. And I'll give you, I'm not going to prove it, I'll give you the idea of the proof. It's not a really hard proof, but I'll show you the idea. So if the limit of your remainder goes to 0, then your function can be represented by a Taylor series. At some point C. Let me give the idea of the proof, okay? Here's the idea. So, idea of the proof. Kind of a skeleton proof. Here's the thing. What we just learned about all this stuff, Taylor series and Taylor polynomials, is that if we represent a function by a Taylor polynomial, if we represent a function by a Taylor polynomial, well, this is not exactly right. In fact, if I represent a function with a Taylor polynomial, it's only an approximation. There's going to be some remainder. The rest, basically the rest of your Taylor series, gets lumped into that remainder. You guys remember doing that? Hopefully, because we just did it, okay? It says, yeah, this is true. It's not really that a function gets represented by a Taylor polynomial. This is an approximation. The Taylor series is what would represent the function. So if it's possible to represent a function with a Taylor series, it's possible to represent the function with the polynomial plus a little bit more, the remainder of that Taylor series. Quick head nod if you understand the idea. This is how we got Taylor polynomials to begin with, okay? Well, if this is true, then if I just do a little bit of algebra here, then a Taylor polynomial should be equal to the function minus the remainder. Shouldn't it? Okay. The only time that this is ever going to work so that the Taylor polynomial represents is equal to the function is if this goes to what?
0.
Yeah. So what the idea of the proof says is, you know what? If this goes to 0, ultimately, then the Taylor polynomial goes to the function. But keep in mind, here's what I'm trying to say. I'm not saying that the polynomial equals the function. What I'm saying is that as n approaches infinity, this thing has to go to where?
0.
Yeah, this has to go to 0 as n approaches infinity. What that means, though, please notice this. What that means, if n goes to infinity, your Taylor polynomial becomes a Taylor series because it's going to infinity. I'm not saying a Taylor polynomial equals the function. What I'm saying is that if I go to infinity, the Taylor polynomial goes to a Taylor series, and if this goes to 0, the Taylor series equals the function. And that's what I'm trying to say. So this right here says that the Taylor polynomial equals our function as n goes to infinity, making this a Taylor series, which would represent perfectly our function. Do you guys see the minute detail I'm talking about here? So this right here is it's obviously not a complete proof, but this is the idea of the proof. The idea of the proof is, hey, you know what? This is for sure true. We can represent a function by a Taylor polynomial. If this remainder goes to 0, well, then the Taylor polynomial equals the function as n approaches infinity. So if this goes to 0 as n approaches infinity, that means n goes to infinity here as well, the Taylor polynomial becomes a Taylor series, and the Taylor series represents our function perfectly if the remainder goes to 0. Show of hands feel okay with the proof. Okay, that's the idea. Now, there's one more thing that we're going to talk about, which we need here, just a little note. It's this note. You need to know that the limit, because we're going to use this at least twice in the next couple examples, the limit of this thing equals 0. Keep that in your memory banks because we're going to use it for a little while. I'll give you the idea here. the idea is, and we've actually seen it before in section 9.8, the idea is this thing right here, if you ignore the limit, the series of this converges. By stuff in 9.8, you can prove that, okay? Series of this converges. If the series converges, the limit of the terms of your sequence has to equal 0. That was the divergence test. You remember doing that? If a series converges, the limit of this goes to 0. We actually used it in reverse. You said if the limit's 0, well, it might converge. Because if it doesn't equal 0, there's no way it converges. You remember that one? You probably used that in some of your homework. So basically, it's from section 9.8. Since this is a convergent series, the limit of the terms of the sequence from which that series is built has to give you 0. We're going to use that in a little bit. Would you guys like to see some examples of why we just learned all this stuff? Okay, so the idea is, now that we know when a function can be represented by a Taylor series, let's see if you even were paying attention, or if you even kind of grasped this. When can a function be represented by a Taylor series? When the remainder when the limit of the remainder
Equals 0.
there you go, that's when. So if we can prove that, then we can prove that a function can be represented by a Taylor series. And that's what we're going to be doing right now. We're going to be using this in some of the examples. So let's do a couple of them just to get our brains wrapped around it. Are there any questions before I continue? Before we continue? We're like a team, like a math team. But I'm the quarterback. Like Peyton Manning.
I'll do the too.
Except not during the Super Bowl.
Yeah.
Not this Super Bowl. The one from, was it 2006 or 2008? Which one did he win? Was it 6? Was that long ago? That poor man. Okay, so here's what we'll do. I want to show that this what is that?
0.
No, what is this?
Series.
What kind of series?
Power series.
Yeah, it is, specifically.
I could tell you what test we used.
I know about that. What series is it? Taylor series or Maclaurin series?
Oh, McLaurin.
Why?
The
Center.
incentive.
Ah, good, Maclaurin series. Is that also a Taylor series?
Yes.
So it's a Taylor series. So Taylor series, Maclaurin series. What I want to show is that this Maclaurin series actually represents, this Taylor series of the function e to the x. I want to show that the Taylor series or Maclaurin series of this function actually represents the function. I know that sounds weird, because some of you say, what? What are you talking about? I know it's weird. It's a weirded word. It's worded weird. But what it means is prove it. Prove that this actually represents this. Now, please do not reinvent the wheel on these problems. Here's what this is saying. Let me kind of break it down to you. Remember that this thing, if you look back in your notes, you're going to see this. In fact, you're going to see that this equals this. Back in your section, whatever you did, with your Taylor series, Maclaurin series, with your Maclaurin series. We're not trying to prove that this is this again. It's already shown that this is this. What we're trying to do is prove that it actually represents it on your Taylor series. So, let me say that one more time. It's already been determined that these two things are equal. What we're trying to do is prove it by showing that the limit of the remainder is what? It's all you're trying to show here. You're trying to show that the limit of the remainder is equal to 0. If you do that, if you show that the limit of the remainder is equal to 0, then you show that your function can be represented by the Taylor series that you were given at C, which happens to be 0 here for a Maclaurin series. Do I need to say that one more time? You sure? You can rewind it. So it's going to be the exact same words. Okay, so ultimately, again, the idea is, look, you're not trying to prove that this equals this by reinventing it. You're trying to prove this equals this by just simply showing that the remainder equals 0. That's it. Okay? So how we go about doing that is very similar to building the Taylor series again. It's just you're trying to find out what the remainder is going to look like in terms of the function itself. So let me show you what I'm talking about. What we're trying to do is this. I want you to show me what this, oops. I want you to show me what this piece is. If we can prove that the limit of this piece goes to 0, then we prove that this representation is represent that function perfectly. That's what we're trying to show. Okay, now here's how we do it. We piece by piece fill this formula out. Now some of it's really, really easy. Some of it says, okay, well, remember that our remainder is always like this. It's always the, if that's n, what's this? No, for remainders, that's n, this is, and this is z. And this is x minus c to the n plus 1, and this is n plus 1 factorial. This should be no surprise. This is the definition of what the remainder of a Taylor polynomial is. You guys with me on this one? I can't afford to lose you now, okay? This should be old stuff for us. Are you okay with it? Mm-hmm. Now, some of the stuff's going to be really easy. You see, some of the stuff is, well, look up here. What's your center? Good. What's your c? So this piece we can take care of. So this goes, okay, well, this is the same thing as something. This will be x to the n plus 1. Do you understand why I got rid of my c here? Yes. The center is 0, therefore I don't even need a c. It's just x. Not sure if you're okay with that one. N plus 1 factorial, well, that's going to be there no matter what. N plus 1 factorial. We don't need to change that. Now, our goal is to find out how much this is, to find out what the n plus 1 derivative of f at z is. So we're going to do that. The way we start with it is we start taking derivatives and find the pattern for it. Hey, that sounds familiar, doesn't it? You've done stuff like that before. So let's start with the function f of x equals e to the x. This is going to be an easy one. You're going to like this. What's the first derivative of f?
E to the x.
What's the second derivative of f?
E to the x.
What's the nth derivative?
E to the x.
Okay, now here's the jump. If the nth derivative of x is e to the x, what's the n plus 1 derivative of x? What's the first derivative of f? What's the nth derivative of x? What's the next derivative after that? Don't be adding ones to that. Did you add a 1 here? No, you don't do nothing. So if this is the first derivative, and this is the second derivative, and the third derivative, and the fourth derivative, and nth derivative, what makes you think it's going to be any different for the n plus 1 derivative? Should it be the same?
Yes.
Have I lost you guys? So we go, okay, well, tell you what. We want to find out what the n plus 1 derivative of f is at z. We just found out what the n plus 1 derivative of f is at x. What must you do now? Change the x to a z. So just plug in z. Therefore, the n plus 1 derivative of f at z is simply e to the z. It's easy, right? Wow.
Then you have to bring a broom in,
I need to buy you an easy button.
sweep up all that corn.
That was even worse. So, that's a videotape now. I'm not gonna edit that. It's a good one. So, what are we trying to do? We're not trying to reinvent the wheel. We don't need to reinvent that this represents this. We're trying to prove it. Prove it by showing that the limit of your remainder is 0 as n approaches infinity. Do that by trying to fill this piece out. This is always where you start for these problems. Always where you start with when trying to prove them. You have x minus c. Hey, it's a Taylor polynomial, right? So you're going to have x minus c. C happens to be 0, x minus 0, no problem. X to the n plus 1. Over n plus 1 factorial, that's your next term. Got it. And then we have the n plus 1 derivative of f at z. This is what you got to work on. So start with the first derivative. Do the second one. Do the third one. Do the nth one. Do the n plus 1 derivative. And then simply plug in z. So far, so good? Now, after that, what we're trying to show is that the limit of this thing goes to 0. This is the idea. Now, you might have some cases here. You see, the thing is that z is always between c and x. You follow? Z is always between c and x. So, if z is always between c and x, how much is our c again? Everybody, how much is our c?
0.
Very good. Why is it 0?
Learn.
Center is 0. So we basically have two cases. So this is 0. We have the case where x is positive, and we have the case where x is negative. You got to show both those cases. Okay, let's start with the, do you guys understand the idea that z is always between c and x? You with me?
Yeah.
C is 0 in this case. So either x is positive, in which case z is between 0 and x, or x is negative, in which case c is between x and 0, because x would be negative in this case. Not sure if you understand that idea. So if positive, what we know is that 0 is less than z, which is less than x. Z's got to be somewhere between 0 and x. Now, if that's true, if z is somewhere between 0 and x, stick with me here, we know a couple things. We know firstly that 0 is going to be less than or equal to the remainder. Look at our remainder. Look over here. Is it true that that's always positive? Is this always positive?
Yes.
Is this always positive?
Yes.
Well, no, but if x is greater than 0, yes, because that's in our case right now. Does that make sense to you? I don't want to lose you guys here. I'm getting some weird looks. So, do you get that this is always positive?
Yes.
Do you get that this is always positive?
Yes.
Do you get that if x is greater than 0, if x is positive, then this is always positive?
Yes.
Therefore, this remainder is always positive right now. Has to be. Now, since this equals this thing, here's where this comes in. If z is less than x, do you agree that e to the z is less than e to the x? Do you agree with that? Then this piece is less than e to the x, x n plus 1 over n plus 1 factorial. Lost you?
I just heard a lot of E's and V's and X's.
Sure. Well, look at the board. This is what we're basing this on, correct?
Yeah.
If this is true, same here, right? If this is true, this is true. If this is true, that's all I'm doing. Exactly the same crap, except this is now less than e to the x. If that's the only thing that's changing, and this is bigger than this, then this statement's true. Does that make sense to you?
Yeah.
Now, here's the idea. If I take the limit of all this stuff, what's the limit of 0? So I'm taking the limit of this as n approaches infinity. What's the limit of 0? Less than this stuff. What's the limit of e to the x, x n plus 1 all over n plus 1 factorial? This is why I gave you that statement just a little while ago. Ignore the e to the x right now because that's not based on n. Here's what this says. Please listen carefully. Pick an x for me. Anything.
2.
In your head. Whatever you want. 4 billion, I don't care, okay? E to the 4 billion is going to be a constant. Do you get me?
Yes.
x to the n plus 1, well, it's going to be 4 billion to the n plus 1. That's true. So you're going to have 4 billion times 4 billion times 4 billion. But it will be a constant for every single one of those fractions. Do you get that? Is that ever a constant? No. So the idea is this thing goes forever. So it gets 4 billion and then it goes way bigger than that. Does that make sense? Ultimately, this limit is going to be 0. That's why I gave you this. Remember doing this? X over n, x to the n over n was equal to 0. I had it on the board. Rewind the tape or look back at your notes. This was 0. If I multiply by something that's going to be a constant, it does not change that. It's still going to be 0. Do you buy into that? Okay, therefore, if this limit gives you 0, and the limit of this thing is 0, oh, tell me what this is going to be. Therefore, the limit of the remainder as n approaches infinity by the squeeze theorem, this says the limit of the remainder of our Taylor polynomial as n approaches infinity must also be 0. Why is that important? That proves it right there. If the limit of our remainder gives you 0, what that says is that for this case, the Taylor series represents our function. That's what it says, because the remainder goes to 0. We showed that earlier. That was the idea of our proof. Now, I got to go through this one a little bit quickly, because I want to do one more example before I let you go. So if x is negative, then x is less than 0, but z's got to be somewhere between there. Well, if that's true, this one's actually a little bit easier, okay, so check it out. If that's true, well, then what we're going to do is we're going to use a little trick here. Remember that if things are convergent in absolute value, then they're convergent regularly as well. You remember doing that?
Yeah.
Okay, we're going to do this. We're going to say, okay, well, then let's just consider the absolute value of our remainder. Is it true that the absolute value is going to be greater than 0?
Yes.
Okay, and this would be the absolute value of e to the z, x to the n plus 1, all over n plus 1 factorial. But this would be less than, check this out, see if you can stick with me here. In this case, z is less than 0. Does that make sense to you? Well, if that's true, then e to the z would be less than e to the 0. You with me on that one? Therefore, e to the z would be less than 1. Does that make sense? If e to the z is less than 1, then what we have is, well, instead of e to the z, we could have the same stuff, but instead of e to the z, we could have what?
1.
Very good. Hey, look at this. What's the limit as n approaches infinity of 0? Oh, come on, everybody.
0.
What's the limit as n approaches infinity of x to the n plus 1 over n plus 1 factorial? Think back to what we did the opening of class. This is 0. So the limit of this thing is 0, the limit of this thing is 0, therefore, and when we do the limit of the remainder of our Taylor polynomial on this case, we get that this is also 0. Whew. That's a lot of abstract stuff, right? That's proving some stuff. That was what we just did. Jamie, go back through it for a few seconds, 10-second little recap here. Okay, 20-second recap. Here it is. The idea of this whole idea is don't reinvent the wheel. You're trying to prove that the remainder equals 0 when you take a limit of it as n approaches infinity. If you do that, what that says is that the remainder goes to 0. Therefore, if I go to infinity, the Taylor polynomial actually represents a function. That's a Taylor series. So, just prove the remainder equals 0. All right. The way we do that is we try to build the remainder into something in z's and x's, not f's. You got to get z's and x's. So e to the z, x to the n plus 1, no problem. Sometimes you're going to have some cases here. In our case, well, x could be positive and x could be negative. We have two cases. If x is positive, z is between 0 and x. If x is negative, then z is between x and 0. Show for both. So you're going to have to use some inequalities here. If z is less than x, e to the z is less than e to the x. Okay, we got that. This limit, the limit of this thing, goes to 0. The limit of 0 is, of course, 0. We know this is positive because z is greater than 0. Therefore, because this limit is mashed or squeezed between these two zeros, the limit of this remainder is also 0. That's what we want, right? We want to show the remainder of 0. Cool. Now, if it's backwards, if z is between x and 0, well, take the absolute value. The absolute value of the remainder is greater than 0. Well, it's also less than 1, because if z is less than 0, e to the z is less than e to the 0. So e to the z is less than 1, e to the 0 is 1. Make this jump. Therefore, e to the z is less than 1, no problem, these things are all the same. The limit of this goes to 0, again we get squeezed through. We get 0, we get 0, our limit goes to 0, and this proves it case by case. So, no matter what, if x is positive, we got remainder 0. If x is negative, we got remainder 0. Therefore, since the remainder is 0, this proves that this Maclaurin series representation actually does represent the function f. That's the idea. It's a long way to show something that we didn't do very much for.
What if we have a function whose nth derivative isn't, like we can't find it?
Then you get a problem. I'm going to show you one right now. Any more questions? I got to erase it to show you the last one. No? Good? That's a good question, because it'd be hard to actually do that. You got to find some relationship for it. I'm going to show you an example like that right now, okay? I didn't mean to just not answer your question there, but I'd like to answer it with this. Okay. Don't worry, this one's quicker. It doesn't look like it's going to be quicker, but it is. Show that that piece of junk actually represents the function. So show that this, whoa, what is that? Maclaurin, Taylor. Does it look familiar to you? This was given to you earlier, so in the last couple sections that we've done. So here's what this says. Show that the Maclaurin series, word for word in English, not math speak, show that the Maclaurin series, which was developed from this function sine of x, actually represents the function sine of x. That's what that says. So show that it's true. The way that we show that this is true is showing that the limit of the remainder of our Taylor polynomial goes to what?
0.
Okay, so what we want to do is we want to somehow find what this thing is. And then show that that goes to 0. Notice something. I don't have to have a 2n plus 1 up here. I don't really care about that. All I'm trying to show is that, remember, the remainder of a Taylor polynomial is going to look like this. It's going to be x to the n plus 1 over n plus 1 factorial. You guys with me on that one? That's what it's going to be. That's going to have an f to the n plus 1 over z. This is where we use this idea. So that's where we get the function coming into it. Now, let's think about this for a second. That's going to be there. This is going to be there. We've got to find an expression for this. Well, let's start with a little bit different of an idea. Let's start with just x. Let's start taking some derivatives, just in our head. What are you going to get for your derivatives? And then? And then? And then? So this is going to either be sine, cosine, negative sine, or negative cosine. No matter what we get, no matter what, we always know that if I plug in any number, I'm always going to get something that's between what two numbers? Let's try that again, because I heard like 15 different answers right now. Okay, do you get that this is always either plus or minus sine? Or plus or minus cosine? Do you guys get that?
Yeah.
Okay, therefore, if I start plugging in, remember, z means you're plugging in numbers, okay? If I plug in numbers here, then what's going to happen is this is going to be a maximum of what number? What's the biggest thing you can get out of this?
1.
What's the smallest thing you can get out of this?
1.
So somewhere, when I plug in numbers, I know that, remember double inequalities like this, -1 is less than this, is less than this. You can make this an absolute value and do this as less than 1. That's by definition what absolute value is. It says, hey, absolute value inequality is a double inequality. That's what that means. So here's what I'm trying to say. We did a lot of math to show something quite simple. Here's the whole point. Do you understand that no matter what my derivative is, this value right here will always be, in terms of absolute value, less than 1. Did you guys get that idea?
Yeah.
The biggest thing can be is 1, smallest thing can be is -1, so an absolute value, it's got to be less than 1. Well, let's go ahead and do this then. Let's set up an inequality. So if I do my absolute value, which is what I'm going to do, what's this always greater than in terms of absolute value?
0, 0.
Yeah, for sure. Now this equals this. Absolute value. But this thing, okay, here it is one more time. Check it out. There we go. Watch, watch, watch. So, if the absolute value of the n plus 1 derivative of f at z is less than or equal to 1, the absolute value of this whole thing is less than or equal to, what's going to change here? Is the x to the n plus 1 going to change? No, we didn't say anything about that. Is this going to change?
No.
Is this going to change?
Yes.
How much, everybody? How much is this less than?
1.
In terms of absolute value, we have that. In terms of absolute value, this is less than 1. Does that make sense to you? Now we get to take the limit. What's the limit
0.
of 0?
0.
What's the limit of this thing?
0.
Told you we were going to use it several times. What's that say about this limit?
0. For the that's 0.
What's that say about this? Does this actually represent our function?
Yes.
If the remainder of our Taylor polynomial as n approaches infinity goes to 0, that means that the Taylor polynomial itself, as it goes to infinity, is a Taylor series, which actually represents our function. And that's how you prove it. You just got to prove that the remainder goes to 0, and we've done that here. You find out, and hopefully Michael answered your question, you find out some relationship. Not necessarily can you find a pattern, there is no pattern. Well, there's a pattern, but none that we would represent mathematically. We go, okay, this is either plus or minus sine or plus or minus cosine. No matter what, if I plug in numbers to it, that's what a z is, it's got to be between -1 and 1. If it is, then the absolute value of that is always less than 1. Use that. Say this is always less than 1, and then show that this goes to 0. Show that, well, it's bigger than 0 if it's absolute value, no problem. Remember, you're always trying to prove it's 0, right? So use a squeeze theorem, but it's always going to be the same number. 0 and 0. Show that that limit of your remainder is somewhere between 0 and 0, and you've proven that the limit of your remainder is n approaching infinity is 0, therefore your Taylor series or Maclaurin series or whatever you have actually does represent the function.